And this is just a list of the different operations. Yeah, if I want to have like the most useful of the top, I want to have a maximum, a minimum, the sum or product. But there's also other operations for reducing things together. Okay, so now remember from yesterday that simple programming example with a polynomial. Yeah, I think you hope you remember. Yeah, and then basically this is, let's see, let's go to, yeah, it's like C++ or something like C. How do I would implement that? Yeah, so I have this ABCD, which is in the vector coefficients. I have xmin, xmax, and the resolution, the number of steps. I put this data in a file, which I called input.dat. Yeah, so I write this in, and then I read from that file with the values. Okay, now I need to determine if I go from the first value to the next one, how much I have to go. This is, I call delta. So I take the maximum value, like I go from here to there, yeah, so I say what is the difference, divided by the number of steps minus 1, and then I get the delta, which is the difference between the different steps. Yeah, and then as I explained in the slide before, maximum is just the smallest value possible. So this is how you do it in C++. You say from a double value, I want to have the smallest, the lowest number. And then you start with the smallest value, and then basically you go from the first number of steps, and then basically for this x, you calculate your formula. You determine, is it a higher maximum, so you store the higher maximum. Then you add delta, and then do the next one. So here you go through all these values. And then at the end, you print out the maximum. Yeah? So now we want to have different processors doing it in parallel. And the way to do it is basically, here's basically all the calculations. So what we want to do now, that instead of one processor going from the smallest value to the largest value, the different processors doing different portions of that data. Yeah? And there's different ways of doing it. Yeah, so I have basically a loop here, which goes from 0 to n, doing some work, and as an example, but it works in all the cases. So this is basically, I have 10 processors, so the rank is going from 0 to 9, and I have 10 values I need to calculate. So the first and most simple version is cyclic. Yeah? So first processor gets the first value, the second gets the second, and so on. When I'm running out of processors, because I have only 4, you start again, yeah? It's 1, 2, like 0, 1, 2, 3, 0, 1, 2, 3, 0, like you go through. So like, give you, it's like giving out cards. And basically, of course, when you have more values than processors, so at some point, not everyone gets values, yeah? Like the first one, he gets 3 values, the second one also, but the second, the third, and the fourth processor only get 2. Because it's uneven work. That's one way. The next one, I'm not going like this, but I'm giving out blocks. You get a first block, you get a second block, and the third block. So I'm doing this way. So yeah, you get 2, and then the last processor gets the rest. Yeah, and this is how you have to write the loop to get basically a distribution like this. Yeah, like this is very simple. You just change the beginning and the increment, and here you have to calculate, yeah, basically what's the block size and things like that. And then, so here's quite an imbalance. So the next thing is, it's called block balanced, which means, okay, I try to kind of do blocks, but that almost equal size. So you get 3, and this one gets 2 and 2. Yeah, and this is how you have to write it. Okay, now basically, in order to parallelize our programs, we have to add the MPI functions with comRank and so on, and then we need to parallelize this loop. Yeah, we go from here to here. And then to keep it simple, I use the cyclic distribution, where I basically this one, because I just have to change the loop here and here. It's more simple. So I basically change my program from here to here. So instead of going from 0, I start with my rank. And instead of going one further, I need to go the number of processors further. So I changed it that. And now I'm running it. So this is kind of simple. It sounds complicated with a work distribution, but especially with cyclic, you just follow the instructions, how to get cyclic, block, or block balanced. But the fun thing is when you run that, you will find out it produces the wrong maximum. So I know it's really hard, but by any chance, I give you 1 minute to look at it. Does someone know why it doesn't calculate the right answer? Yeah?
Because each process will have its local maximum. So each one will be, I guess, different for each one.
No, it's not. You're close to it, but the problem is I start with Xmin. And then every process starts with Xmin. So instead of basically different people doing different portions, everyone is actually calculating on the same X. So everyone is just using, like on 4 processors, a fourth of the data, but everyone is calculating the same thing, and we're ignoring 3/4 of the data, but everyone is calculating the same. So what we actually have to do is, instead of doing the Xmin before, you have to say, oh, I'm starting with Xmin plus so and so many steps. So that everyone is doing on a different portion of the data. The problem, and this is here where you see, this is where the why parallel computing is harder than sequential computing. Finding these, like if you write a new program, it's typically simpler. But often people tell you, oh, here's a program some student wrote 5 years ago. It's not fast enough. Change it to run in parallel. But you don't know that program very well. So you have to go through all the lines and saying, like you look for loops to distribute. And then in each loop you have to say, how do I have to change that to split up a work distribution and so on. This is just a pointer, an example. But over time you learn about that. Okay, now we can put it together. So again, this is, let's look at, this is the same thing in Fortran. And that's the same thing in Python. This is the Python version, but it's basically just written in a different way. But I wrote examples in the slides in all 3 versions. So you basically look at the version you are most familiar with. Okay, we also saw yesterday, this is the blue stuff we have to do. Okay. So now it doesn't fit on 1 slide anymore. It's actually 2 slides. Okay, all the blue, again, is the additional stuff. So we need, in addition to the coefficients and the max, we also need to store my rank and the number of processors. And then I did another optimization. Like before we had Xmin, Xmax, and the number of steps. If I want to basically read this data and send it to all the processors, I have to do 3 times a broadcast, who is like kind of expensive. So what I do here is I take these 3 values, put them in a vector. The first one is the Xmin, the second one is Xmax, the third one is the number of steps. And then I can send the vector with 1 broadcast. This is kind of an optimization, but so just to let you know. And then, as I said, we get what's my rank, what is the number of processors, and then we read the data. And as I explained yesterday, typically one process is doing it, and we're using number 0 because that process is always there, independent how number of processes I have. And then basically, if I'm rank 0, basically I read the file and I read it into basically the variables. Yeah. So basically, the rank 0 is doing this, and when reading the data on the other processors, basically we ignore that and we go to a broadcast. But the broadcast basically automatically is synchronizing. Yeah. So like the broadcast waits, like the root process is sending it, and all the others are waiting until the data is there. Yeah? So basically, the root who is reading it sends it to other data, and the others kind of automatically stop here until the data is here. Yeah? So you don't have to do synchronization of barriers. Yeah? So it's working automatically. So just from time to time, like wiggle on the mouse and okay. So, okay, now we have to send our coefficients. These are 4 integers. So we say the variable coef, these are 5 double values. Yeah, like 5.7 or what n. And the root process, because he's reading that, is sending it to everyone in ComWorld. When we do the same thing for the domain, so in the domain variable, these are 3 doubles, we're sending it from 0 to MPI ComWorld. And then after that, every process has these values, yeah, as a copy of that. Then we do this, what I just explained before. So the red portion is, yeah, basically changing, not going from 0 to n, but from my rank, and you add some processes. This is the other to get the logical error done, yeah, that you always start with a different x. And then we have to, yeah, basically now everyone is working on a different portion, and now your comment comes in. So we need another variable because we only calculate the local maximum out of the data we have seen. So we store it in a new variable called Lmax. Okay, when everyone is done with this calculation, we need to get the global maximum. We use the reduce function. So I put in my local max, I get out the global, yeah, my local maximum, I get out the global one. This is 1 double. I use the maximum function to reduce, and the 0 process is getting the result from everyone in ComWorld. Yeah, and then if you're 0, you print out the maximum is like this. And then I finalize and I'm done. This is basically how it's working. Yeah, and it's the same thing in Fortran and in Python. Okay. So that's basically what other people at least learn in a week, squeezed together in 1 hour. Yeah. As I said, the goal here is not to basically make you MPI experts. So I'm not expecting you when you go home and change your program and make it parallel. The idea is basically that you get, what does MPI mean? It's a library, what is a message, what's a collective operation, what's a communicator, yeah? And then if you're reading a book or you're watching an online tutorial, you have a start and you know already the basics, and then perhaps it's easier to understand an online tutorial or so. Or ideally, your university or some local compute center offers an MPI class for 3 days or so. You go there, and again, you kind of have a head start for the others, and you know a little bit more. Okay, just when you're wondering, like, okay, this is everything I need, what is in MPI 2, MPI 3, and MPI 4 and 5? Yeah? Just so, in MPI 2, they also added things to do parallel I/O. So how can I write 2 files in parallel? How to do one-sided communication. So I'm not sending a message, I'm just putting a value into the other's processor memory without telling him. Then in 3, you had neighborhood collectives, non-blocking collectives. In 4, you have persistent, partition communication, MPI sessions. And then in 5, yeah, you see lots of stuff. But this is all advanced stuff for special cases. yeah, to make the program even more optimal and efficient for very specific situations. In general, you basically only need the stuff in MPI-1. Okay, so summarizing it together, what's about MPI? So the advantage is it basically gives you a library for parallel computers, which gives you functions to communicate, to synchronize, and do I/O functions depending on your need. Like, yeah, I have this special case where I have functions there. Every company who is producing parallel computers, Fujitsu, Cray, Intel, HPE, whatever, they all typically provide you with an MPI library which is optimized for that specific computer. Yeah, like the Fujitsu MPI knows exactly like this six-dimensional torus on the Fukaku and make sure the message is sent in the most efficient way. You don't need to care. You always use MPI send from here to here. And then the vendor and the library takes care of the rest. If you have a laptop or you don't have a huge cluster, there's open source versions available. And there's even two. There's MPI or MPICH and OpenMPI. They are both equally good. Pick one you like, and then you can download, install it, and just because you have multiple cores on your laptop, you can do the same exercises on the laptop like in a parallel computer. It's just basically say you have a quad core or an oct core. You shouldn't use more than 4 or 8 processes. Yeah? You should not use more cores, no more ranks or processes than cores. Yeah? But at least like the quad core, you can speed it up by 4 times if you're lucky. Just about the size, MPI-1 has about 129 functions, and the latest version, I forgot to calculate it for MPI-5, but MPI-4 has now 664. But as I said, typically, this is the nice thing is, you pick out the functions you need for your special case and application area, and you typically just need these 20, 30 functions. Yeah? And once you learn them, you can use them. And so it's not too bad. Yeah? So you don't have to use all of MPI or need to know all of MPI to use it. The disadvantages, this is not so much MPI, this is the disadvantages of distributed memory programming. Yeah? You have to change your program where you say, how do I distribute the data? So which processor is working on which data? You can even complicate it, yeah? Because sometimes the memory in each processor is not large enough to get all the data. Here we just have a few numbers, but you have a huge matrix. You even have to say, okay, the first processor gets just this slice of a matrix. And you have to write all the I/O that the different processes are reading the different slices. And then you have to, oh, here I need to synchronize, here I have to do broadcast, reduce, sending messages, and so on. And it's your responsibility. Yeah, but the computer does only know what, he's dumb. He does what you're doing. Yeah, but you have to see it a different way. You are the king. The computer can do anything you want. The problem is you just have to tell them what you want. And you have to learn how to precisely tell them, because he's dumb. Yeah? Because if you say something, you could do it like this, yeah, the computer can do it. And if you say the wrong thing, he does the wrong thing. So but if you know what you're doing, it's really powerful. And it works on sequential and parallel versions. You can run it just with one process when you run it on a single processor, or you can run it with 10,000. Yeah? And it runs on shared memory system, in a node, across multiple nodes. So MPI programs always work if you want to do parallel. So this is a good idea to learn at least some basics of MPI. Okay, no, it's fine. We are at the end of MPI. Okay? I guess at that point you don't have much questions yet. In the afternoon, after lunch, we will try to basically take this Hello World program and change it a little bit. So you have to, not just copying it and running it. So I ask you to change it a little bit and then run it on Fukaku. And then probably questions come up and then we solve it in the afternoon. Okay. So in the last half hour before lunch, I want to basically, how does that look in OpenMP if you do shared memory computers? Okay. So now, program models 2. Okay, again, what does it mean to do parallel programming inside a node? This is internode programming. We do with OpenMP, and I probably do that basically. And this one, like a little bit about if you have GPUs and Python. I probably have a time for lunch. I quickly do that, like in the first, say, 20 minutes after lunch, and then we do the exercises. Okay. So, what is the difference now to distributed computing? The thing is, yeah, like before that, you had the different threads on each processor, and each has its own data. Now we have shared memory, which means you just have a big block of data in one memory, and then you have your thread going on. And it's just that basically you start basically with one, and then if you need to do it in parallel, you kind of split up and say, now I'm starting and so on, and now I need 3 friends. Come, and then you all of 3 work together, and then you continue, and they can go back to whatever, do something else. So it's kind of like writing a sequential program, but from time to time, you get extra help. And so basically you are kind of a sequential thread, and then if you need extra work, you create extra threads, yeah, like calling your friends. And you have memory, so you don't have to split it up. But sometimes, like your different friends, your different threads, want to calculate the same thing, but with different data. So you need kind of to have a separate thing. So this is called private data. It's like the my ID and the numprocs. Yeah. So every thread wants to have its own ID. Yeah. When you create copies in the global memory for each thread, and this is called private because it's just for one thread, and if everyone is using it because you're just reading it, then it's called shared data. And you will get it later when I show an example. And you can do it in different ways. You can do OpenMP. You can, there's also a library called POSIX, or some compilers even have something like autoparallelization. You just say, run this program and try to use as many threads as possible, and it automatically parallelizes your program. It works for simple cases, or if your program is written in a good style, but typically it's better if you help him basically by using OpenMP. Okay, so OpenMP. Again, it's a community standard, but it's only for shared memory programs. Yeah? It does, in red, it does not work on a cluster with different nodes. You can use it in one node of a cluster because it typically has more than one core, but you cannot use multiple nodes. And then the difference is it's not a library, but it's so-called directives or pragmas. So what is directives and pragmas? So you basically think about it like that. You write your program, and every time you want to do something in parallel, you make a comment. And that comment has a specific structure. Yeah, it's not just like, oh, I want to do something in parallel, but you have to write it in a specific way, but it's basically a comment. And when you compile the program, it normally ignores it, and when you get a sequential program, but if you're using an OpenMP compiler, it finds that comment, and then it changes your code around automatically to do the parallel stuff. So you're not basically saying how to be done, but you say, this section I want to do a reduction. Here I want to do, like this and this. And then he writes the code. So it's a little bit simpler than MPI. Yeah? You only say, this is what I want to do, but you don't have to specify the details how to do it. This is what the OpenMP compiler does it for you. And it only works because inside shared memory it's simpler. And everything, again, you find in openmp.org. The problem with his comments is, again, you need to know what you want, and you have to specify it in the correct way. So if you're specifying something wrong, the compiler believes you and changes your program to do the wrong thing. It's not automatically correct. Yeah, the compiler always believes you. Yeah, so you have to put in the correct comments and the right comments. Yeah, and otherwise you get problems. Okay, again, a little bit history. It started out very early. There was the first version, 97 for Fortran, 98 for C. And when new version came out, when they realized, oh, it's almost the same, so at 2005, they combined it. And then again, since then, we are adding and adding stuff. Again, I tell you basically, again, how it's basically version 2 or something we need here. Okay, so what is basically we use in OpenMP? So you have these comments with directive pragmas to specify what portion of a code should run in parallel. Yeah, this is called a parallel region. It basically says from here to here, please use additional threads to do work. Then when you come to loops, you can say, oh, this loop should be done in parallel and different people should pick up different pieces. Yeah? But you don't have to specify the work distribution, you just say, make this loop parallel. And when a compiler does all these changing of cyclic and distributed for you. Yeah? So this is typically for, like most our HPC programs are matrices and vectors, so you typically have loops. So basically with regions and loops, you can do a lot of things already. Sometimes you have more graphs, and when different threads should work on different portions of your graph or nodes, then you can use tasks. And they support GPUs by, you can say, OpenMP, load this thing onto the GPU and do it on the GPU. So this is target offloading. And when you need something, again, to say, oh, only one process is doing it, you need something to say what is shared, what is private, you need reductions and also a synchronization, like barriers or so. Okay. And then there's some functions also. There is two functions, which is basically the comsize and comrank. So one is OMP get num threads, which gives you the number of threads in your current run. And OMP get thread num is basically your number. Yeah, it's like the rank. And then there are some environment variables and so on. Okay, so now basically this is the main slide to explain how it works. So I write a program setting A to 1, setting A to 2. When I have a loop from 0, I from 1 to 9, and for 1 to 9 I calling some other function to work on it. And when I set A to 3. When I compile it and run it without special thing, it creates basically, a sequential program has one thread, it just executes this code, like it's written here. So now I'm adding, say, okay, actually this portion from here to here, I want to do in parallel. So I make this special comments, and then what happens if I run it with 3 threads, basically, okay, just the first one is doing the sequential portion. Here you go you fork, you expand, you get additional threads, additional friends, but it just says go parallel. So this thing, like each of them is doing the same thing, just 3 times. Yeah, it's not very helpful, yeah? Like everyone is setting A to 2 and everyone is going from 1 to 9. But if I'm saying, oh, please make this loop parallel, yeah, you have to do another comment here. Then it basically says, okay, this one is going from 1 to 3, the next one 4 to 6, and the last one 7 to 9. Yeah? So by changing that, you just basically say, here I want parallel, and I want to make this loop splitting up, and you're done. It's much, much simpler than MPI. But it only works in one node. Okay, so how does it look in C? There's a special header again, OpenMP.h. And then basically in C, you say hashmark pragma. So you always have to start with hashmark pragma. And they say this is an OpenMP pragma. And then you say, okay, this is parallel. Yeah? And then you have to say from here to here, and you use the parenthesis like doing blocks in C. Yeah? Like you say, this is the beginner function, end of a function. Say, okay, this parallel region goes from here to here. In this parallel region, yeah, we call the function OMP get thread num, and this is my ID, and OMP get num threads is the number of threads. And I can again print out, hello, I'm 5 out of 7. Yeah? If you would call them here before the parallel region, everyone would say, okay, I'm running with 5 threads, but everyone would say, I'm 0, I'm 0, I'm 0, because you're just in the sequential one. Yeah? You have to use these functions inside a parallel region to get useful results. This is in Fortran, and then, sorry, there's no Python. So there's some people from Intel and other people who are working on some unofficial Python extension. I forgot what it's called, which allows you also to do like these special comments for Python. But I couldn't make it work here on Fukaku yet. It's just it probably works on your laptop. So perhaps next year in the next school they have it working on Fukaku, and I can also use it in the examples here. So if you want to do the OpenMP example this afternoon, you have to do it in C, yeah? Or look for someone who can help you. This is just basically how in task is doing, but this is advanced. I'm skipping over that. Okay, now again, I have my program. I have to compile it. You just use the compiler to optimize it, but you have to basically tell the compiler, I have OpenMP comments in my program. Please don't ignore them, because normally comments are ignored, but basically do these transformations for me. And again, this is not standardized. Every compiler has a different option how to activate this OpenMP mode. Yeah, for GNU, it's -F OpenMP. For whatever, Intel is -Q OpenMP and so on. And again, you have to look into your documentation. How is this OpenMP flag called? And I tell you in the afternoon, what is the flag for Fujitsu compilers? It's -K OpenMP. Yeah, okay. Yeah, and then basically, there is no special MPI run or S run or something, because it's just a normal program. You just call it, you run it. But how do you tell how many threads do you want to use? So what you do is there's an environment variable called OMP underscore num underscore threads. You set this environment variable to the number like 8, 16, and when you start it, the OpenMP reads this variable and uses so and so many threads. Okay. Same thing here now, yeah? Like I have my hello world program. I set the environment variable OMP num threads, so I have n cores. It runs it, yeah? It creates a copy of that program, the sequential thread. When I'm executing it and I'm coming to this parallel region, I do some calculations, but it's only working on that one core. When I'm coming to, now I want to go parallel, OpenMP creates also threads here, but they only execute what's inside this parallel region. Yeah, they say take the code here, and also basically you launch it once, and then each parallel region is launched onto the other threads. Yeah, so you go, launch it something on all processors. You go again sequential, launch a second thing in parallel. There's always like going out, in, like fork join it's called. The problem now you see here, yeah, you have only one copy of my ID and n threads, because the default of data is shared. Every thread is using it. But if you're doing that, basically, everyone is printing out something, depending which order, who is calling OMP my thread number before the print. Yeah? So what we have to do is we have to tell that the myID functions, because it's different, we want to have it be different on our processors, we have to declare that this is private. Yeah? And then basically when we're running it, yeah, and I'm doing this, it creates, at least for this parallel region, copies of this MID, and then we get different numbers. Yeah? This is the difference between shared and private. And you probably see it, actually I think I put it in the hello world. Yeah, it says run that in parallel, and for this parallel section, make the myID and threads private. So which variables do you need to set private? You have to set the variables private, like in that region where you write into. If you're just reading, everyone is reading from the same one, but you have just look in your parallel region, which variables I'm writing into, which means typically every thread needs to have its own value, and when you make these private, you just add them here. And if you forget them, you get some wrong number. Okay, and then again we want to do our maximum polynomial. Yeah, remember basically we're reading, this is, the maximum polynomial. Yeah, we read the poly.dat, and now I'm using the C version, not the C++ version. I do a fopen, fscanf to reach the coefficients, the xmin, xmax. Yeah, and it's black, so automatically this is the sequential thread doing it. Yeah, the sequential thread is setting ymax to the smallest double value. It calculates the step, and only the loop we want to do in parallel. And when I say, okay, yeah, this is Pragma OpenMP parallel, because it's the loop is one construct, I don't have to put extra parentheses here. This means the next command after it, or the next thing after it, is in parallel, so I can even save adding additional parentheses. And normally I would have to say OpenMP parallel, and then Pragma OpenMP 4 to make this loop parallel. But because it's happening so often, there's a shortcut where you can say Pragma OpenMP parallel 4. So this makes a parallel region, and it has to be a loop, and then and parallelize also the loop. Not just making. When you just say here without the 4, every thread would calculate the same thing. By doing 4, it splits up the data distribution. Yeah. So I say OpenMP parallel 4. Because we write in X and Y have to be private, and here you have this reduction. Everyone is doing it, and at the end you want basically here in Ymax the overall reduced value of all the maximums. So you say the Ymax is a reduction variable, and the operation to reduce together is max. And then you're done. So in MPI, we had to write lots of functions. And here I just basically adding a comment, and I say, okay, we should be parallel. This set should split up the loop to different threads, and this variable should be reduced. And you make one comment, and your program runs in parallel. This is an extreme case because it's just a nice, simple example. Yeah, and so normally you have to add in your programs a few more of these pragmas. Yeah, typically all the loops you want to parallelize, you have to add that comment. But compared to MPI, it's much simpler. Yeah, and the main thing is you only say, I want that parallelized, or I want to have the loop run in parallel, but you don't tell it how. The compiler can do it. It's smart enough. Yeah. Okay. The same thing in Fortran. I said, okay. In Fortran, it looks like this. But yeah, and now, if I don't say anything, OpenMP uses some undefined way what he thinks is how he should split up the loop. Yeah? But if you say, oh, I'm an expert, I know a little bit better, I want to have like cyclic or something, you can actually do that. You can say, yeah, if I want to have cyclic, you say, I want to have a parallel loop with a schedule static, comma 1. Static means I split it up before I run, and everyone, I turn out 1, 1, 1, 1, 1, 1, 1, 1. Yeah? If you want to have it in a blockwise, you say just static. Everyone gets one block. What's not specified whether it picks the block or the block balanced. This is not specified. Yeah? But you can say whether you want to have it cyclic or block, and depending on the algorithm, sometimes this makes a difference. You just specify, and if a program runs fast enough without saying, you can just leave it off and leave it to OpenMP to distribute up. There's also more complicated ways of distributing data, like dynamic and guided, but this is actually if you want to optimize your program and so on. Okay, and this is how to do in Fortran. Okay, what else do we need? You typically also at some point need a barrier. So you're in your parallel region, inside the parallel region, and you have a first phase and a second phase, and in between you want to make sure everyone is done with the first phase. You want to have a barrier function. And you do the same thing, you have pragma OpenMP barrier. And at that time, it does this barrier for you. Yeah? Then you want to have, sometimes you have things, you adding things up. Yeah, it's like you have a variable and everyone says, now I'm adding 1, and another one is adding 1. So you want to make sure only one process at a time is make this addition or doing something special. When you can mark, it's called a critical region, you can mark that region with critical, and then basically the compiler makes sure that the first one can do it, but when the second one also wants to do the same operation, he has to wait until the first one is finished. Yeah, so it does one by one. But don't do it that often, because if you do everything in critical, then you go back to sequential, yeah, because it's one after another. If you want to have something in a parallel region, which only one processor is doing it, and you don't care which one, but you only have to do it once, you call it single. Yeah? It's not needed very often, because at begin and the end, or outside of parallel regions, it's automatically single. Yeah, it's just when you have a large parallel region and you, instead of stopping the parallel region, and then you do your single thing, and then you start another parallel region, because every time you make a parallel region, you have to get the other threads involved. Yeah, sometimes it's just, okay, I have as many friends, and then it's just a small portion where like some people don't have to do anything when you make this single. So here, basically the first one who comes there does it, and if you say, oh, I want to have a specific thread doing this single thing, you can say OMP mask, and then basically specifying a filter, which one of the threads is doing this single portion. This is not yet supported by Fukaku. So for Fukaku, you have to say OMP, pragma OMP master, and then automatically the 0 process is doing it. Okay, that's it. Advantages, like MPI, it's a stable standard, it's well defined, it's all supported by all computer and compiler people. Yeah, Fukaku, Intel, GNU, all of them support OpenMP. It's kind of a small number, especially like the basic person called pragmas, you can add to your program. The nice thing is, you can do it step by step. In MPI, you have to change the whole program that it does MPI. Here, you can say, okay, I have my program, and then it's not fast enough, but you know, like here, this phase, like the third step, takes a lot of time. So you just make it that section parallel, and you still have a working program. The other stuff is done by one thread, and when you come to the thing where you need more, it's using more threads. And then like 2 weeks later saying, oh, it's still too slow, oh, when I parallelize another loop and another loop. So you can do it one step after another, but all the time you have a running program. Yeah, it's not as fast, but you have it working. The disadvantage is it only works in a node. So if a node has enough memory and the stuff is fast enough, fine. You just work with OpenMP. Yeah, you can sometimes takes a day to parallelize like this little program. The problem is at some point you need to go to like larger systems, and then OpenMP doesn't help you anymore. Then you have to go to MPI and do the full thing. At some point you had special compilers, but now GNU supports it for like years. The problem here with shared memory is there's two problems basically. You don't declare the right variables private. Yeah, and then the different processes override that value all the time, and you don't notice. And also, like you forget a barrier or something, and then basically the second process goes into the next phase, and the others are not finished yet, and so it uses some of the shared data, and it's wrong. The problem is, the programs typically still run, it's just the result has the wrong numbers. So you'd have to, it's always also for MPI, it's always good to have an idea. You typically don't know what the result has to be, yeah? Otherwise you wouldn't need a program. But you probably know, okay, like say I'm calculating some speed. So the speed should be never negative or something, yeah? And things like that. So you could add at the end a few simple checks that you get at least a warning if something goes wrong, yeah? But if something goes wrong here, it's really hard to find. That's the problem. Okay. Okay, yeah, 2 minutes, and then we can go lunch. Yeah. So, as I said, all modern computers have nodes, and each node is a shared memory computer. So what you typically want to do is, I mean, you can use MPI, and then basically it ignores that inside the node you have shared memory, and you basically every core runs its own MPI process. The problem is then there's typically just one network interface in the MPI, in the node. And if you have like large nodes, like Fukaku has 48, all 48 messages, like all the messages from all the 48 cores have to go through this one network interface, and then it's a bottleneck. So what you typically do is, yeah, you're using actually both. So you use MPI to basically create large blocks of your distribution, and you're sending messages in between. And then inside each of the blocks, you still have loops over these blocks. Then you use OpenMP inside the node to use addition, like the threading. Yeah. The problem is now you have to use MPI and OpenMP. You can make errors in MPI, you can make errors in OpenMP, and you can make errors by combining them. Welcome to parallel computing. Okay, and as I said, you have different methods. You can use MPI and OpenMP, you can do MPI and POSIX threads, MPI, and sometimes like there's already libraries who use OpenMP inside. So use MPI, but when the threading is done by the math library or something, yeah. But yeah, and then if you have additional accelerators, then you need even more. Yeah, you need a multi-threaded program with accelerators, or you need MPI plus multi-threaded plus accelerators. And I think I do that after lunch. That is too much. There's probably another 10 slides. We do that. Okay, I think perhaps like one quick question, so we have some time for lunch.